A graduate student builds mock skies, injecting fake voids into simulated large-scale structure and ray tracing CMB photons across them. She tweaks profiles, depth, sizes, and watches the temperature imprint shift by microkelvins. The numbers drift toward but don't quite reach the observed cold spot. She sends the plot to her advisor. Close, not enough. The reply comes back. Good. That means we're measuring. And this loops us back to boundaries. Voids, cold patches, filaments, they all speak in the language of light. Photons ferry the evidence. If nothing outruns light, then the shape of emptiness is set by what light can cross and what it can't. Where signals can't go, nothing can be asked. Where signals skim edges, boundaries matter most. Under-rendering isn't the right frame. Latency is. If you can't send the request, you can't expect an answer. Which is why, to see how far that rule goes, we have to follow light to its speed limit. Latency of reality, the speed of light as a hard cap. While that debate over void simmers, the real arbiter of what can be asked and answered is speed, specifically, the speed of light. C isn't just a number, it's a contract. It caps how fast information moves, which means it caps how quickly reality can coordinate itself across distance. If you think in render terms, C is your maximum frame sync rate for the universe. Start local. Your light cone is the set of events you can influence or be influenced by. Draw a point for you, then a cone opening forward in time for what you can touch, and a cone opening backward for what could have touched you. Anything outside those cones is off-limits. Not later, not with better tech. Off-limits in principle. That's latency baked into geometry. Space and time mix so that any path trying to outrun light gets pushed outside the cones and loses causal contact. Now scale up. Expansion stretches the grid itself. Galaxies don't rocket away through space faster than light. The distances between comoving markers grow. That's why recessional speeds can exceed c without breaking the rule. You still can't send a message faster than light to catch a fleeing galaxy if the expansion between you grows too fast. The metric gives you horizons because even a photon sprinting at c through the local fabric can't make headway against the global stretch. That's where the event horizon shows its teeth. Beyond it, no signal you send now, not even light, will ever arrive. Meanwhile, something else is happening across town in the gravitational sector. Gravitational waves ripple at light speed too. When neutron stars collide 100 million light-years away, the space-time tremor that eventually whispers through a pulsar timing array left long before we were born. Those arrays are patient ears. They watch for tiny shifts in the ticking of millisecond pulsars, searching for nanohertz waves that take years to cycle. It's a human lesson in latency. You set the experiment, then wait for the universe to answer on its schedule. Here's a micro story. A team calibrates a radio telescope at 3 a.m., sipping lukewarm coffee, chasing picosecond jitters in pulsar pulses. They know a wave, if it exists, will show itself as a correlated drift across the sky's clocks. Months pass. Then a hint, a common spectrum process. They don't claim victory. They add stations, extend baselines, push noise down. The signal strengthens. If it holds, it's proof that even gravity talks at sea, within the same horizon logic that hems in light. Latency isn't just delay, it's structure. Think of the cosmos as a network with finite bandwidth and bounded round-trip times. You can't coordinate a galaxy cluster instantly. Filaments form because gravity's pull adds up over time, not because distant masses negotiate outcomes in real time. Causal patches evolve semi-independently, and only where light and gravitational influence have had time to shuttle information do you get synchronized stories. Where the ping time is longer than the age of the system, the conversation never finished. That's not a glitch, it's the design constraint. This decision would haunt our expectations because it means global now is a myth. There's no universal present that renders in one sweep. Each observer's slice of spacetime is stitched from signals that actually arrived. Your now includes a star as it was years ago, a quasar as it was billions of years ago, and your own hands as they are. Reality is a mosaic assembled at light speed, with expansion stretching the tiles. If no request can be sent, no response must exist for you. That's the stakes line. You can't demand a pixel where no signal can, even in principle, fetch or verify it. In a bandwidth-limited, latency-bound universe, rendering is just the stabilization of facts within reachable cones. Outside, the best you get are priors, symmetry arguments, statistical expectations, consistency constraints. The map beyond your horizon isn't blank, it's inferred. It carries no more detail than your physical channels can justify. There's a flip side that makes the world generous. Within horizons, facts get broadcast redundantly. Photons scatter off a table into countless directions, encoding the table's location and color into many independent channels. That redundancy is how you and I agree on what's there without sharing minds. It's also why the energy ledger stays balanced. Creating objective facts is copying, not inventing. Copying takes time at sea and leaves trails you can cross-check. One last connection to carry forward. Photons and gravitational waves obey the same boundary logic. Both respect light cones. Both define what can be known and when. If horizons are interfaces, these are the messengers that patrol them. And if latency rules reality, then the universe didn't forget to render your far field. It's still in transit. Pixels in the dark, holography, Planck scales, and discreteness. Boundaries keep showing up, so the next question is obvious. Underneath the smoothness, does spacetime come in pixels? People point at the Planck length, about 1.6 times 1035 meters, and the Planck time, about 5.4 times 1044 seconds, and say, there's your grid. Careful. Those scales mark where our current theories stop making reliable predictions, not a proven lattice. They're thresholds that say, new physics lives here, not rulers etched into reality. Still, black holes hint at something radical. Take a black hole's event horizon and ask how many possible internal configurations it could hide. The entropy, the count of microstates, goes like the area of the horizon, not the volume inside. 1/4 of the area measured in Planck units. That area law isn't a vibe. It's a precise relation pulled from thermodynamics and semi-classical gravity. It says boundaries carry the bookkeeping. However you encode the interior, the maximum information scales with the surface. Holography turns that hint into a principle. In a set of theories we can solve, the anti-de Sitter ones, everything that happens in a gravitational bulk is exactly matched by a quantum theory living on its boundary. Geometry and gravity on the inside, quantum fields without gravity on the outside, 1-to-1. Our universe isn't shaped like those toy models. It's closer to de Sitter, and we don't have a complete holographic dual for it. But the area scaling lesson keeps showing up. Entanglement entropy of regions follows area laws in ground states. The guts of spacetime seem built from correlations that live on cuts and edges. If that's true in spirit for our patch, volumes might be effective. The inside behavior could be emergent from fewer degrees of freedom stitched along surfaces. That looks like compression again. You don't need a voxel-by-voxel ledger if the boundary data and consistency rules determine the bulk to the precision anyone can test. Not sloppy rendering, economical encoding. So where are the pixels? Experimentalists went looking. If spacetime had a grain, maybe high-energy photons from distant gamma-ray bursts would arrive out of order, with tiny dispersion depending on energy, like different wavelengths in glass. So far, null results. Photons across huge energy ranges arrive in step within tight bounds. Others tried interferometers to catch spacetime jitter, holographic noise, subtle positional fuzz at Planck scales. Clever setups set upper limits, but no confirmed wiggle. Smoothness holds, at least where we can measure. Here's a micro story. A small collaboration builds an instrument that cross-correlates laser beams to hunt for correlated flicker, noise that can't be blamed on the table, the air, or the mirrors. Months of data, careful subtraction, a winter of doubt. The final plot shows no excess. They publish a bound, not a discovery. It's not defeat. It narrows the map of what discreteness could look like and pushes candidate models to respect Lorentz invariance and known dispersion limits. Maybe the mistake is thinking pixel, the way a screen has pixels. Quantum gravity candidates, loop gravity, causal sets, spin foams, do talk about discrete structures, but they don't predict a simple grid. They predict spectra of areas and volumes, or partial orders of events, or networks whose coarse-grained behavior becomes the smooth metric we measure. The discreteness, if real, might be relational and hidden, not a visible checkerboard. Smoothness could be the signature of strong compression. Only long wavelength, low curvature modes propagate cleanly, and the microscopic mess averages out so well you can't shake a telltale shimmer loose. Black holes keep pressing the case for boundaries. Hawking's calculation made horizons radiate. The temperature, Gibbons, Hawking for cosmological horizons, Hawking for black holes, ties thermodynamic notions to spacetime itself. A horizon with a temperature has entropy. Entropy means microstates. Where do those states live? All roads point back to surfaces and entanglement across them. The interior is less a storage locker, more a region whose properties are encoded on or reconstructible from the edge, depending on the observer's access. There's also the page curve story waiting down the road. Information that falls into a black hole seems lost if you only trust Hawking's early calculation, but newer tools using quantum extremal surfaces show the entropy of the radiation rises then falls, as unitary quantum theory demands. That revival says the outward streaming quanta carry correlations that, in principle, let you recover what fell in. Again, the surface ledger knows the tale. Boundaries tally, bulks comply. Notice how this changes rendering. We don't need spacetime to pre-store every microscopic detail in the volume. We need enough edge data and consistent rules so that any accessible bulk question has a definite, stable answer when asked. If discretization lives at Planck scales, it's hidden behind an extraordinary compression ratio. The lack of flicker isn't proof of continuity. It's proof that whatever the substrate is, it respects symmetries and cancels noise to a degree that beggars our instruments. Here's the stake. If bits scale with area, your world's maximum distinct information is finite for any finite horizon. A de Sitter, like Cosmos, hands you an entropy bound for your causal patch. Try to stuff more independent detail inside than that, and physics will push back, by thermalizing, by collapsing, by decohering and dumping heat. The horizon is less a wall and more a quota. And experiments haven't cornered the answer. No dispersion means one class of models is squeezed. No holographic jitter means another is pushed out. Yet black holes, entanglement, and thermodynamics keep whispering the same refrain. Boundaries encode, volumes emerge. If compression hides the pixels, then the universe's smoothness isn't a bug. It's the most efficient outcome allowed, which makes inflation's role as the first great compressor the next place to look. Inflation's pen, writing the first lines of the map. To see why the sky looks so well organized with so little time to spare, we need to go back before there was a sky in any normal sense. Inflation is the move that sets the board. For a sliver of a second, space itself expanded at an outrageous, accelerating rate, exponential growth that took a tiny, causally connected patch and blew it up to cosmic size. The payoff is simple to say and subtle to live with. Regions that look too similar to have ever talked at light speed actually did, before inflation stretched them apart. Here's the first consequence. The horizon problem, why the cosmic microwave background is the same temperature in opposite directions of the sky, melts. Those regions were neighbors in the pre-inflation patch. They exchanged heat, settled into near-uniform conditions. Then inflation pulled them far beyond each other's light cones. What looks like an impossible coordination across billions of light years becomes a memory of a smaller, causally connected beginning. The second consequence is flatness. Curvature dilutes under rapid expansion the way wrinkles smooth out when you stretch a sheet. The universe we see is close to spatially flat because inflation ironed it. You don't need to fine-tune initial curvature. You need enough E-folds, enough doubling steps to wash it away. That's a compression trick, too. Take a messy starting state and leave behind only the largest scale, simplest features. But the move that matters for structure is the quietest one. Quantum fields fluctuate. Even in their lowest energy states, they jitter. During inflation, those microscopic jitters got stretched to macroscopic scales. Modes that started smaller than an atom became larger than a galaxy. When their wavelengths outgrew the horizon, they froze. Their amplitude stopped oscillating and imprinted as slight differences in density and curvature. After inflation ended, those frozen ripples re-entered the horizon and gravity went to work on them. You can hear the imprint in the cosmic microwave background's acoustic peaks. The early plasma of photons and baryons rang like a drum. Some ripples were caught at maxima, some at minima, some halfway. The pattern of peaks in the CMB power spectrum is a fossil sound wave chart, and it lines up with an origin in inflationary fluctuations, nearly scale invariant, slightly tilted, Gaussian to first approximation. A handful of numbers, the amplitude, the tilt, the baryon fraction, the dark matter density, describe it. That's inflation as a pen with a fine tip, writing a sparse instruction set that expands into a detailed cosmic web. Here's a micro story. A theorist scribbles ns approximately 0.965 on a whiteboard, the spectral index's value measured by Planck. Not exactly 1, slightly less. That small tilt says long waves have a bit more power than short ones, matching simple inflationary potentials. It's a whisper from a field we don't yet know by name, telling us the slope of the hill it rolled down. Now, honesty check. Inflation is a mechanism class, not a single theory. Many potentials can drive it. Some predict small primordial gravitational waves, a curl pattern in the CMB polarization called B modes. Experiments have chased that signal and set upper limits. So far, no confirmed detection. That squeezes models with large field excursions. Others survive. The search is ongoing, and that's good. It keeps the story anchored to what the sky allows. Subtle anomalies hang around the edges. The CMB shows a low quadrupole power compared to naive expectations. There's an alignment of low multipoles, an axis of evil in some papers. That might be noise, might be a hint. Hemispherical power asymmetry, maybe. These are low-significance curiosities that don't overthrow the core, but they do whisper that the initial conditions might carry features beyond the simplest toy. A bump in the potential, a brief interruption in the roll. Respect the whispers without mistaking them for shouts. Then there's eternal inflation, the idea that while our patch ended inflation and reheated into the hot Big Bang, other regions kept inflating, budding off bubbles with their own properties. It's a provocative edge case. If true, it seeds a multiverse where our observable domain is one pocket among many. Do we have evidence? Not direct. Some models predict collision signatures, bruises on the CMB from bubble-bubble contacts. Searches have turned up no solid scars. So we file it under speculative edges, consistent with the math in some regimes, unconfirmed by the sky. What inflation does give us with confidence is a data compression origin story. A tiny patch, smoothed and stretched, with quantum noise promoted to classical seeds. The universe didn't pre-store every detail. It recorded a minimal set of correlations and let gravity, radiation, and chemistry elaborate them. That's efficient encoding. The acoustic peaks are your checksum. The large-scale structure is your decompressed file. There's a practical stake. If the initial write was compact, then everything we see, galaxies, voids, clusters, comes from evolving those few parameters within tight constraints. When JWST surprises us, we tweak subgrid physics under those constraints. When we map a giant void, we test whether it fits a Gaussian seed field. When anomalies tease us, we ask if a small feature in the pen stroke could explain them without wrecking the peaks. The ledger stays balanced. The code stays lean. Hold this frame as we turn to black holes. If inflation wrote the first save file on a cosmic boundary, black holes test whether the universe keeps its records when matter falls off the map. Boundaries, entropy, information. They're about to collide in a decades-long argument that taught us how fiercely the cosmos guards its bits. The black hole accountant, information, firewalls, and retrieval. If inflation wrote a sparse instruction set, Black holes test whether the universe ever throws the manual away. Stephen Hawking's calculation said black holes radiate, slowly, thermally, without memory of what fell in. That was the spark. Thermal radiation looks like noise. If a pure quantum state collapses into a mixed thermal soup, unitarity breaks. Translation: the cosmic ledger loses bits, and physics hates that. Here's the setup. A star collapses, crosses its Schwarzschild radius, and a horizon forms. Hawking pairs pop at the edge. One escapes as radiation. One falls in with negative energy, shrinking the hole. The outgoing quanta in Hawking's first pass carry no imprint of the star's microstate.